So we will proceed with our study of geometric algebra through the spacetime algebra. And we left off last time deep in this section on multivectors. And so how this paper is actually organized is it talks about multivectors and it leans on bivectors because for the spacetime algebra, bivectors and their product with vectors is something that's very important. How we understand that product to work is critical. I've already made the case that we need to understand how all of the different blades can be spacetime multiplied with all of the other blades. So they start with bivectors and vectors, which we've already studied. And then you see later on that here's bivectors with vectors. Then they study bivectors products with other bivectors. So they delay that for a while, right? And you never see anything like bivectors with trivectors and all of these other things. And this is because they're creating a structure that's going to make all of that a little bit simpler, but is very particularized to the space-time algebra. So the approach that I had earlier was a little bit more general in principle. You know, I was talking about how this would work in multiple dimensions or higher dimensions. And here they're going to focus on keeping it simple for the purposes of space-time algebra. And that's fine. So we're going to mimic that. But the way they do this is they introduce bivectors, then they start talking about reversion and inversion, which are operations related to multivectors. However, keep in mind that all multivector operations, there really is only two. There's space-time product and there's addition, vector addition. You can add multivectors together and you can take their space-time product. Everything else is somehow derivative from those two things, in particular derivative from the space-time product. So when I write A dot B or even A wedge B, I'm talking about the symmetric and antisymmetric parts of the space-time product of two multivectors. And, you know, it's not sure which is symmetric and which is antisymmetric. That does change depending on the multivectors you're dealing with. But these are derivative from the space-time product. Likewise, they're going to describe things they call reversion and inversion. And those are operations that you can execute on a multivector. But ultimately, that all refers to space-time product in some way. Then what do they do next? They're going to talk. It's worth our while to look at how now we are prepared. We understand enough that we can now look ahead and see how this paper is organized. So let's spend a quick moment doing that. So reciprocal bases, components, and tensors, they're going to make contact with your standard tensor calculus or tensor analysis or tensor algebra. The theory of tensors, right? And components, we've actually discussed components a little bit, so they're going to repeat that. The reciprocal basis is an important idea that's going to end up looking a lot like the dual basis in our previous work on tensor spaces and their dual spaces. Then after that, then they really dig into the pseudoscalar. And the whole value of the pseudoscalar is to execute Hodge duality and complex structure. And we'll see little hints of that in this lecture when we look at one of their tables that reveals all this stuff. But the pseudoscalar's big function in a lot of the work in this paper is to execute Hodge duality and create a notion of complex structure in a couple different places. Then they dig into bivectors again. So bivectors, they kind of introduce it here, and then they really dig into this so-called canonical form of a bivector. So that'll be interesting to see. When I use the word canonical, what I mean is it's something that's kind of forced upon us, right? We don't have to make any choices. And they're going to introduce a form of the bivector that is very reasonable, and we don't have to add anything to the theory to create this particular form of the bivectors. But do not This word form does not have anything to do with one forms, two forms, and three forms, the dual to one vectors, two vectors, and three vectors from exterior calculus. This is just the canonical way of writing a bivector. Then they finally attack bivector products with bivectors. And then once they do that, everything in the space-time algebra is under control, because they're going to create a system where trivectors are actually vectors through this Hodge duality. So you never need to worry about multiplying things with trivectors per se in the structure that they're offering up here. Well, we talked about it when we kind of spoke in full generality of things. Well, if you have complex structure, then you have complex conjugation, so they'll talk about that. Then they'll talk about relative frames and paravectors. This is a really important formalism. Here's the Hodge duality formalism. This is going to be a formalism, a duality that's based on gamma 0, right? Whoops. So gamma 0, and gamma 0 has a unique role in all of this stuff because it is the only space or time-like basis vector, but it also really defines the observer's inertial reference frame. So this whole notion of paravectors, relative reversion, and the space-time split, big deal. And it's a form of duality. So it's the second form of the duality. Hodge duality is one form of duality, and this space-time split depends on a second duality that we'll talk about. Then there's a whole sector called bivectors, the commutator bracket, and the Lorentz group. And this is probably where I will pause to talk about the notion of rotations in the geometric algebra. How do we rotate vectors? How do we rotate, if we rotate the coordinate system, how do we rotate these vectors? Or in this case, I think we'll do it actively. We'll be rotating the vectors and the bivectors and the trivectors inside our geometric algebra. And how we execute those rotations is very important. And then spinor representation and the Pauli and Dirac matrices, I guess this is where they're going to make the connection between the gamma matrix, the gamma unit vectors and the gamma matrices of Dirac, which will be very interesting. Okay, so with that review, let us continue just reading the paper. So the last time we left off with this paragraph where they talked about the algebraic trace operation, which is really collecting the scalar parts of multivector products. And this algebraic trace was, I think that's the last place we stopped. And then they mentioned the Dirac matrix representation, which they'll talk again in section 3.8. Then there's, in the stream of the text, a few tables appear. And you're tempted to look at these tables. Like you're tempted to really look at table 2. And what you'll see is things that you've been introduced to and things that you haven't, right? Like we now know that their notation, this is a notation table. And I love notation, so I'm happy to look at it. But you'll know some of these things we've seen, right? So now we know that all scalars will be Greek letters. Great. We know all 4 vectors will be Roman lowercase letters. Both the Greek letters for scalars are lowercase too. Bivectors will be bold uppercase Roman letters with straight structure. So they're block, bold, Roman, and they're the bivectors. Now pseudovectors, look how they write the pseudovector, right? They're giving it 2 parts. The first part is a lowercase Roman letter, and then the second part is I, and we know what I is. I is gamma 0, 1, 2, 3. So we haven't learned this part yet. We haven't learned about how we're going to write pseudovectors as though they are vectors multiplied by the pseudoscalar. And ultimately, but we know pseudovectors are grade 3 objects, right? So these are all of the grade 3 parts of any multivector is the pseudovector part. So we haven't learned yet, but we have learned about the pseudoscalars, right? A real part times this pseudoscalar basis vector. So we know about pseudoscalars. Multivector, we know the symbol for a multivector is just a Roman uppercase letter. Then there's this notion of a complex scalar and a complex vector. So we have not studied those two yet. The complex scalar, though, we've been sort of foreshadowed into it. We already know about the real number, and we know about the pseudoscalars. So obviously, just by looking at this, I can see that a complex scalar is the addition of those two. I already know that I does square to -1, so it certainly works like the complex imaginary number I, but it's not. It's this quadravector. It's this volume, unit hypervolume. So clearly, we've got some learning to do there, but it's already like not that hard because I can almost figure out what that has to be. Two one-dimensional objects added together. Likewise, a complex vector, well, I don't know yet how these pseudovectors work, but I see I'm adding a vector and a pseudovector. I know it's a pseudovector because it's got the same form as this entry in the table, the pseudovector entry. So apparently there's some complex structure to make there, but it's a complex vector structure. So that's kind of interesting. I can't wait to figure that out. And then they talk about the gradient and the tensor adjoint, which we have not seen yet at all. So then the next section of this table, what else? What here have we seen already? Well, we've seen the orthonormal basis vectors, right? We have not seen the reciprocal basis, but it's pretty clear. This definition is pretty straightforward, right? The reciprocal basis vector of gamma mu is going to be gamma mu inverse, and we're just going to write it with gamma mu with an upper subscript. It's very reminiscent of covariant and contravariant basis vectors, right? So that's cool. But we have not been introduced to that yet, so I'll leave that in a little green mark. Relative three vectors, don't know what that means because three vectors, so three vectors in our business is a pseudovector, right? In other words, this is a language problem, right? Pseudovectors are all of these objects that are constructed out of a grade 3 thing, right? That's a pseudovector. Now that is a 3 vector. We call this a 3 vector. When we have a construction like the wedge product of 3 vectors together is a 3 vector. Nohowever, this notion of relative 3 vectors, something's up there because notice the notation goes back to our classic notation from vector algebra with a little arrow on top, right? So these relative 3 vectors are not the same as this thing. So this is a language issue, and they've already prepped us because they know that they're talking about, when they talk about the trivectors, they're talking about grade 3 objects, and these 3 vectors are your classic 3 vectors, but somehow embedded in the Clifford algebra. So we'll learn about those later, but they are fun. And then they have the orthonormal basis for 3 vectors. So obviously, if these are vectors, they must have a basis. So evidently, they will introduce us a basis. Relative 3 gradient, relative time derivative. We don't know about any of that stuff. Scalar components. Well, that we do know about. I've already mentioned, and I think I've even screwed up, F mu nu, gamma mu wedge gamma nu. Right? These are components, and they're scalar components. And what they're saying here is when we deal with scalar components, Greek letters mean it goes from 0 to 4. Roman letters, it's just the spatial parts, 1 to 3. Minkowski metric tensor, we got that. The Euclidean metric tensor is also the Kronecker delta. And the antisymmetric Levi-Civita symbols are here. So this is just a sort of a notational thing. The point is even though we're in the middle of this paper, it's okay to dive into these tables and see, well, what do I know and what do I not know? And it's a good way to track how you're proceeding with understanding the paper. Eventually, you should understand everything on the paper if you want to be really comprehensive, or you just select the parts you're interested in. Like we might stop after we understand the space-time algebra and not worry about the space-time calculus, for example. We will worry about the space-time calculus because ultimately our goal is to understand Maxwell's equations. But once we do enough space-time calculus to see Maxwell's equations, I'm not convinced that we'll go to the end of this paper together at least. And then the next table, they are basically showing various physical quantities that are modeled by blades of different degree. And so charge, mass, and proper time, that seems logical that they're modeled by scalars. What's modeled by a pseudoscalar, though? Magnetic charge and something they're calling phase. So there are real things out there called pseudoscales. Now, in the physical world, we don't know if there are magnetic charges, right? But if there were, they'd have to be pseudoscalars. Now, vectors are your anything that's a 4-vector that you learn from classic special relativity is still a vector in the Clifford algebra. The bivectors, electromagnetic fields, well, you know, we understood the electromagnetic field to be a bivector even in our study of Maxwell's equations via differential forms. So that's not a big surprise. Angular momentum, torque, and vorticity, okay, not completely sure that those are going to fit super solidly into the electromagnetism formulas story that we're talking about, but certainly classical physics, as long as it happens in space-time, in the space-time of special relativity, this Clifford algebra should be able to handle it. And certainly all of these things are, you know, they're part of space-time physics, so they should be in there. And they get linked to bivectors. Pseudovectors, the magnetic potential, the magnetic pseudocurrent, and the helicity pseudocurrent. Not sure what helicity pseudocurrent is, but these other things, they are pseudovectors. Not surprisingly, they involve magnetism, because we know the magnetic field has always been a pseudovector, so it's not a surprise that these guys are too. So this is just sort of to show you that, hey, physics does map on to this structure. The next table that they show, this is a really fun table or picture, because it really shows you how to take the space-time product of a vector with a bivector, right? We need to know how to do that. And I think it's worth going through this table even though we haven't reached this part of the text, just because, hey, here it is, and it's in front of us, and it's really glorious, right? But the idea is that F is your bivector, and you notice that on this side of the equal sign, they don't give F any defined shape, because it doesn't have a defined shape. It only has an area and a circulation. And it also has an orientation, right? By orientation, I mean it's got components in the basis of bivectors. So, for example, you know, F has got to equal, in this case, I'll just say one example, it's going to be F12 of gamma 1 wedge gamma 2, right? And that's it, right? So this is the sort of the orientation of the plane. Now, it could have more complicated orientation, or it could actually be, right now it's depicted as a simple bivector, right? If it was a not simple bivector, and I don't know if there's a word for that, there would be another little area segment with an orientation, or essentially in an orthogonal space relative to AF, and it would be floating out there separately. It turns out 2 is the most you need, right? Every bivector in the Clifford algebra can be made into the sum of 2 simple ones. Even if it's, you know, if you write down F mu nu gamma mu wedge gamma nu, no matter how many F mu nu components are not 0, ultimately you can rewrite this as the sum of just 2 bivectors. Anyway, that aside, this question is, what is the space-time product? How do we understand the space-time product of a vector and a bivector? And here's your vector A, and here's your bivector F. And there's, you know, looking at it from a purely geometric point of view without any reference to coordinates, meaning I'm not going to introduce any gamma mu's into this analysis. I knew that the vector A certainly can be broken down into a part that is parallel to the bivector and a part that's perpendicular. The parallel part is called the projection, and the perpendicular part is called the rejection. And the way we want to understand this is that, well, look, there is some vector in the world, C, where if I just take the projection of A and I sweep it along C, the area that I sweep out will be the area of F, whatever F is. I have to find this vector C such that C, well, A parallel wedge C equals F, right? If I can do that, well, I can do that, and when I do that, that vector C is uniquely defined. And and you'll notice the way they've done this in the picture. They say this equals this, because this area has no definition. We could define this area we can define the shape any way we want. The area is well defined, but the shape is indeterminate. So why don't we just establish that the shape is going to be a parallelogram, and one side of the parallelogram is going to be the projection of A that is part of this space-time product. That's really easy to do. So now I'm talking about the space-time product of A with the projection of A wedged with this new vector C that's defined such that the area of A parallel wedge C is equal to the area of F. And then I say, well, that space-time product is going to have a vector part and a trivector part, because that's the way space-time products work with multivectors, is they have parts that lower the grade and parts that raise the grade. Sometimes they have parts that leave the grade alone, but not always, and in this case they don't. Whenever you multiply by a vector A times any multivector M, right? Where if this multivector, well, let's say a multivector of grade, 7, you're always going to have a part that has grade 6, and you're going to add to that a part that has AM grade 8, right? You're going to have two parts. So whenever you have a vector multiplying some blade, you're going to have a blade of one lower degree and a blade of one greater degree. So in our case, we have a blade of grade 1, and a blade of grade 3. So this vector C, well, that's the answer to what is the lower grade blade. This is the contraction. They call this the contraction because you're contracting the blade to a lower number. They call this the inflation because you're inflating the blade. But the inflation is really easy. You just take F in whatever shape it is, and you just drag it along the rejection of A, and you end up with this little three-dimensional volume. So that's really a nice way of looking at the picture. I don't think I need to read this caption except for one thing. They always say a space like F is in an oriented plane. And they talk about the space-like vector. And I'm not quite sure why they do that, except there's nothing about this analysis that demands that anything here, either the bivector or the vector itself, be entirely composed of gamma 1, gamma 2, gamma 3, and have no component in the time-like direction, right? So space-like usually implies that we're dealing with just the space-like basis vectors. Now, I think the reason they're saying space-like is because they want to draw it in space. So they're saying, okay, we're just going to look at the space part so we can draw it, because they don't know how to draw something in time. Although, I got to say, in special relativity, we always write space-time diagrams like this, and we have no trouble talking about paths in space-time with time as one of the axes. And nothing about this analysis will really change if you have a time-like component to the vector A or a time-like orientation to the bivector F. But they just want to emphasize, in this case, space-like, but that's not a requirement for anything. It's not a requirement for any of this, that anything be space-like. This is the general way of interpreting this, interpreting the space-time product of a vector A and a bivector F. I guess what they're saying is it's hard to do this kind of spatial interpretation if you're dragging something through time, because what's a parallelepiped in time, right? So, but, you know, I'm used to kind of picturing those things from general relativity, right? I have no trouble picturing things, 3 volumes where one of the sides of the volume extends in time. Anyway, so that's this beautiful picture. I really love this picture. I think it's a great way of understanding the space-time product of a vector and a bivector. Well, it's not a great way, it's the only way, but it's very well drawn and well explained. So to continue, all proper physical quantities in space-time must either correspond to pure k-blades or multivectors that combine k-blades of differing grades. Right, so that goes back to that chart we did before where all the physical quantities were attached to different blades that would model them. These are the only frame-independent objects permitted by the constraints of general relativity. So, hence the expansion of a general multivector into its blade parts indicates the full mathematical arena in which relativistic physics must occur. The algebraic structure allows us to manipulate each of these proper objects with equal ease and finesse. All right, that's the promise of geometric algebra. In space-time algebra, it promises that all of special relativity and all physics done in the arena of special relativity is handled by the space-time product of 2 multivectors and addition between multivectors. That's what it's saying. There's also space-time calculus that needs to be introduced. That was those gradient things. But ultimately, those operations with calculus are still firmly attached to the space-time algebra. We'll get there eventually. The added complication of multivectors in C13 over the original 4 vectors of M13. Remember, we all learned special relativity right in here. Everything we did was inside M13. Now, this paper is saying, not good enough. You should have been doing it here. And yeah, there's some added complications, and that may seem excessive, and it may be intimidating, but the added structure contained in the full multivector is necessary for a proper description of space-time quantities. And what they're getting at is that, yeah, you can sit around and say, hey, B, the magnetic field, that's a space-time quantity. Yeah, it's a vector, but you know what? It's a pseudo-vector. So don't forget, it's a pseudo-vector. Well, if you attach B, if you understand how pseudo-vectors are constructed, now in the space-time algebra, you don't even really have to remember that it's a pseudo-vector. You just have to understand that B is attached to, say, trivectors. Although this paper will formulate it differently. I guess what I should back this up a little bit. Pseudo-vectors have a home in the Clifford algebra that is not ad hoc. Everything has a place, and there's a place for everything that matters. So indeed, as we will see in more detail in 3.4 and 3.6, each distinct blade of a general multivector is in fact a familiar type of object that appears in the standard treatments of relativistic physics. We summarize several examples in Table 3 for reference. Well, we've already looked at Table 3. The multivector construction unifies all these quantities into a comprehensive whole in a principled way. Well, the notion of a principled way is a little bit vague, but basically I believe what they're after here is, look, we built C13 in a purely mathematical way from the ground up using the logic, using nothing more than the logic of abstract algebra, really. And we interjected it, the minimum amount of physics that we know about, namely the Minkowski metric. And then from the abstract algebra plus the Minkowski metric, that's those are the principles, right? And yet, this thing actually does a great job modeling reality. And it's not like we literally built it and kludged it together to model reality, sort of like the epicycles of Ptolemaean astronomy, right, where everything went around the Earth, and they make a great model of things going around the Earth, but that great model was just really kludged together. This isn't kludged together. This is actually built from basic vector space principles and the Minkowski metric, and voila, it all falls out. So it's a comprehensive whole because it covers everything, but it's not just a bunch of stuff thrown into a box. It's well organized from first principles that shouldn't necessarily obviously tell us about the real world, but it does. Moreover, the Clifford product provides them with a wealth of additional structure which we will exploit to make manipulations of multivectors simple in practice. And that's I think what they're referring to there is the beautiful simplifications that they're going to do to keep us away from having to think perpetually in terms of this mess, right, and getting much closer to this. And we're getting even simpler. We've already gotten simpler, right? Because this is now I, right? And these trivectors we're going to see are going to become things like gamma 0 I, right? And things of that ilk, right? I think this one is probably gamma 0 I, right? So, yeah, I mean, you can already see it, right? Gamma 1, gamma 2, gamma 3 times gamma 0, right? Let me clean that up a bit. Gamma 0 times I is gamma 0, gamma 0, gamma 1, gamma 2, gamma 3. Well, gamma 0, that just goes to 1, right? And you're left with gamma 1, gamma 2, gamma 3, which is what that is. So we're even going to get rid of gamma 1, gamma 2, gamma 3, and we're going to probably end up writing just gamma 0 I for that. But stay tuned for that. Stay tuned for that. But the beauty is they're saying is that space-time algebra has some real efficiencies in it where we can just grind this down to a beautiful, simple notation. And I'm looking forward to seeing it and to sharing it with you. And okay, so we finished that. So now they do their section on bivectors. Let me see if we have enough time to do some more. Yeah, sure. So we've seen all this. So this should go quite smoothly for us. This is our second approach. We've already worked hard. We know how to take bivector products with vectors. I've already told you that this formula, A times B wedge C equals A dot B C minus A dot, C B, which I got it right this time. That's worth memorizing, right? And this is a bivector product with a vector, right? So we already know. Just to be clear, this is the grade 1 part, right? The grade 1 part. The grade 2 part is A wedge B wedge C, right? Straight up. The grade 2 part's always easy. Let me just write that a little more clearly, right? This is the thing I said, oh, you should memorize that. That's the grade 1 part. This is the grade 3 part. So let's see how they present it here. It should look a lot like what we did because I learned it from this kind of stuff. And I'm repeating back to you what I've already read in advance, and then we're going to read it together. And that's the kind of way we're going to go through this whole paper, right? We will see in the following sections that several dualities of space-time algebra allow a complete understanding in terms of scalars, vectors, and bivectors. That's kind of what I was getting to a moment ago, right? The trivectors can all be written as vectors times the single pseudoscalar basis vector. So we kind of lose trivectors as their own entity eventually. But we haven't done it yet. There are several dualities, and we have to study those still. I'm only aware of 2 dualities, so I don't know about several. Maybe I've forgotten some. Out of these 3 fundamental objects, bivectors are the least familiar, so we'll make an effort to clarify their properties as we progress through this introduction. Well, by now I'm hoping that you all are not unfamiliar with bivectors. Bivectors are interpreted as an oriented area, simple as that, an area with a circulation. And bivectors are written as wedge products, and the area of this wedge product is derived from the components of A and the components of B in a given basis, and it's a parallelogram, A swept along the direction B. So I have a vector B and a vector A, and I sweep A along B, and I get a parallelogram, and that area is the area of the bivector, and the circulation from A to B is the circulation, and it just sits there in space as appropriate. So that space, sitting in space by being oriented with B here and A here, right? A and B. So those two vectors are sitting in space. We have no trouble with that. So orienting the plane is pretty easy because it's the plane spanned by the two vectors. Totally simple. So it is least familiar, but we've been talking about it so much that it's not least familiar. And if you came here from exterior calculus, actually, if you came here from the exterior forms, if you came here from our study of differential forms, there is a problem because differential forms are not interpreted this way. Differential forms, dx wedge dy, that is not a little element of plane. It's not interpreted as a little element of plane. In fact, it's interpreted as something that would be cut by little elements of plane, right? It's understood as essentially a honeycomb in space. And dx is not interpreted as a little pointy thing in space. Even though dx lives in a vector space called the covector space, you cannot interpret it as a pointy thing. And in fact, what you have to interpret dx as is as a series of little planes that have a density, right, but no extent, meaning the distance, these planes have no extent, but they do have a density in this direction. And a vector, as I've drawn it here, can cut a bunch of planes. And some vectors cut more planes than others. But that's how a single form works. And two forms would be a bunch of planes in one direction and a bunch of planes in another direction forming a honeycomb, right? And a honeycomb can be cut by a little piece of plane. How many honeycomb segments does it cover, right? So differential forms and exterior products of vectors are interpreted very differently. So if you're coming from that place, then two vectors and three vectors are in fact a little bit unfamiliar because you don't use them as much in other studies. Anyway, moving on, we now consider how bivectors and vectors relate to one another in more detail, defining two useful operations, contraction and inflation, in the process. It is worth emphasizing that all operations in spacetime algebra are derived from the fundamental vector product and sum. So they're introduced for calculational convenience, conceptual clarity, and for contact with existing formalisms. So that's what we were getting at with, you have a vector, bivector, spacetime product. This is the fundamental product. This is considered the contraction and inflation piece, and they're introduced just to help us understand this product. But they have to be understood, and you have to be able to calculate this and calculate this to build this. But it's a way of getting us to ultimately building the space-time product. That's kind of what they're saying there. But a product between a vector A and a bivector F can be split into two terms, vector and trivector, in an analogous way to the product of vectors. Because this looks like our vector expression, but this is not a dot product. This is not a Minkowski contraction between two vectors, right? Such as it would be if this was AB equals A dot B plus a wedge B, right? This would be a Minkowski contraction. Here it's not. It's something that is a little more artfully defined, but we've already gone through it, right? I've already shown you how to do that calculation. But then they point out that in this case, the contraction part is the anti-symmetric piece, and the inflation part is the symmetric piece, and I showed you that several lessons ago. Notably, the grade-lowering dot product or contraction is anti-symmetric, while the grade-raising wedge product or inflation is symmetric, which is opposite to the vector product case. Yeah, exactly. Now, this is a trivector, which is totally anti-symmetric, But it is the symmetric part of the space-time product, and I showed you why a couple lessons ago that actually makes sense. Because if you're going to flip A and F, if you're going to flip that to FA, right, it takes two flips to do it. And if F is B wedge C, then this is A wedge B wedge C, and to flip that to the front takes two flips, and you lose your sign. So you need total antisymmetry over here to capture the symmetry of the vector-bivector product. The geometric meaning of these products can be ascertained for space like F by decomposing the vector A into a rejection and a projection parts, perpendicular and parallel to the plane. After factoring F into its constituent orthogonal vectors, into any constituent orthogonal vectors, F equals BC, we can write out this expression. Oh, so this is a nice algebraic expression of that picture we saw. Notice the first thing they do is, after factoring F into constituent orthogonal vectors, that you can always do this. F is a bivector. It equals some vector B wedge C. But it could equal literally any two vectors B wedge C as long as they give you the same area. So let's just assume that if all we know is that we're dealing with a bivector, let's just assume that B and C are orthogonal and that B dot C equals 0. Look how nice that is. Now F is B dot C, but F is B wedge C, but B dot C is 0. And let's see how we use that. Well, if B dot C is 0, then, well, what is the space-time product of B and C? Well, that's B dot C plus B wedge C. But as I just said, B dot C is assumed to be 0 because we're constructing F out of orthogonal pieces. So everywhere I see B wedge C, or everywhere I see F, I can replace it by the space-time product of B and C. So AF now becomes ABC, and FA becomes BCA. Really, really beautiful stuff, right? And so now I break up A into the projection and rejection. So A now equals A projection plus A rejection. We do this a lot in E&M. You always do the parallel electromagnetic field and the perpendicular parallel electric field and the perpendicular electric field. And they transfer differently relativistically, but you can always do this, break this up. And so everything being linear, we are going to say that, what we're going to say is that this is going to, actually, looking at this, they've left out quite a few steps here because they're not very difficult steps, but I think it's worth filling in the gaps as our last part of today's lecture. So let's look at this formula very closely. It's pretty easy each step, right? The first step is A, right? A here is replaced by A parallel plus A perp, right? Guaranteed easy step. BC, we've already understood how F is replaced by BC, and that goes right here. So that's all easy. So I just blow that up by linearity. So I'm going to do this totally step by step. We blow this up by linearity. So now it's A times A parallel times the space-time product of BC plus A perp times the space-time product of BC. And A parallel and A perp, they're just vectors, right? Two vectors that add together to form A. So then I take the space-time product of BC, and I'm going to bust it out into its antisymmetric and symmetric parts. B and C are vectors, and they're orthogonal. Remember, we've decided that we're making F out of two orthogonal vectors. So I can add that the Minkowski contraction between these two vectors is 0. So this step is purely formal in the sense that it's basically adding and subtracting 0 to BC and getting this symmetric and antisymmetric split. And we do that for this BC on the perp side and the BC on the parallel side. So that and that expression are the same. But we know that B dot C is 0. But we also know that B dot C literally equals BC plus CB over 2. It's the symmetric part of the space-time product of the vectors B and C. So I know this is 0, and I know this is 0, right? Because that was part of our assumption in this process. So now this reduces to a parallel times the antisymmetric part of the space-time product of B and C, and a perpendicular times the antisymmetric part. So the final form that they leave here is, you can see, there's the antisymmetric part multiplied by a parallel. So we've actually got this piece down. We're done with that piece. Then this piece is a little, it's not that hard to understand, right? We just realize that B and C being orthogonal, I know that the space-time product of B and C of BC is going to equal B wedge C, because B dot C, which would have been the scalar part, well, I know that's 0 by assumption. So I replace BC with B wedge C, and likewise CB gets replaced with C wedge B. And that's in this perpendicular part. And oops, I made a little mistake here that I just cleaned up. So don't ignore the part that was just sitting there before, because that doesn't belong. But now I have the space-time product of a vector with a bivector, space-time product of a vector with a bivector. And I know how that works because I've taught you how that works, right? So this is going to be the dot product of the perpendicular part with B times C minus the dot product of the perpendicular part with C times B. And then this part has its own version, right? And then the trivector part, this expression here, a perp space-time product B wedge C, has a perp wedge B wedge C as its trivector part, and minus a perp C wedge B is minus a perp wedge C wedge B for its trivector part. Now these two trivector parts will add together and double, because what you're going to, and this I think is, it's all over 2, right? Both of these terms are over 2, because this part here is about to double, because you're going to flip C and B, and then you're going to change that sign to a plus, so you're going to get a 2 out front. So what you're going to get left with is plus a perp wedge B wedge C, with the 2's cancel. This stuff here is all 0, because A is the rejection off the BC plane. By definition, it has no projection in the B direction. If it did, it wouldn't be the rejection from the plane. So likewise, it has no projection on the C direction either. So every one of these dot products is 0. So this entire term goes away, and what you're left with is this. The parallel part times the antisymmetric piece of the space-time product of BC, and the perpendicular part of A times the wedge product of B and C, which is exactly what which is what they came up with here, right? For this section right here, right? This here is BC minus CB over a half, right? So with that in place, you can see that if you switch this, nothing different happens. You just end up with the stuff on the right-hand side. Now, notice that this is exactly a description of what those boxes were all about, right? This is the trivector part, and this here is a vector. Because remember, this is, maybe it's not so obvious that this part is a vector, right? Because this is the antisymmetric part of the product of 2 vectors, right? So being antisymmetric, this is going to be B wedge C, and this will be a parallel space-time product B wedge C. But that's going to break up into a parallel wedge B wedge C. But a parallel wedge B wedge C has got to be 0, because a parallel is in the plane of B and C. And therefore it's not linearly independent, and you can't make a volume out of it, right? It's a flat plane. So that whole thing's going to be 0. So all that's left is a parallel dot B C minus a parallel dot C B, right? Which is going to equal this vector, right? So that's a vector. So this guy here is a vector, right? And it reflects that picture we saw earlier. Okay, so it was worth the exercise of kind of digging into the mechanics of how this calculation was made. And so their approach is, well, they did this for AF and they came up with this, and then they switched it and they did it for FA and they came up with this expression. Well, then they just said, well, we're going to take the A dot F to be A parallel dot F and equaling this expression right here, which we already know, we just used it, and A wedge F is going to be a perpendicular wedge F, which is this expression. So when you see the dot product of A with a bivector, basically that equals the projection part of the vector dotted into the bivector, and it equals this expression that we've learned long ago. And if you see A wedged into a bivector, you can forget the projective part and only look at the rejective part, and that forms this beautiful little trivector. And this is just another demonstration of how all of this works. And what do they say? They say for space like A, B, and C, these expressions have intuitive geometric interpretations. The contraction produces a vector in the plane of F that is perpendicular to A parallel. And indeed, choosing B equals A parallel, so that F equals A parallel C, which is that C vector we were talking about, yields A dot F equals C, right? That's all from this picture we studied here, right? A dot F is C. And here now we choose F equaling A parallel times some vector C, and this vector C is one of the pieces of our space-time product of A and F. And the other piece, of course, is F in any shape, just drag through the rejection part of A. And that's the last thing they say here. The wedge product produces a trivector with a magnitude equal to the volume of the parallelepiped constructed by dragging the plane segment F along a perpendicular vector A. These constructions are all illustrated in Figure 3. So we, again, got a little bit ahead of ourselves there. Doesn't matter whether you learn this from the figure or learn this from the text. They're both very comprehensive. Okay, so that takes us through their section on multiplying vectors and bivectors. And you should be good at that now, right? That's a thing we have learned. Notice they didn't use any basis vectors here, so this is all a proper demonstration. But when you do a proper demonstration, you are allowed to break it up into this parallel and perp part. But that is always relative to just some arbitrary bivector F. So you don't even have to be too specific. If you gave F components, then A parallel and A perp, you'd have to figure out the parallel and perp components of A. So here it's actually simpler to avoid all that. So the next section, we're going to introduce some operations called reversion and inversion, and we'll just proceed down all of these papers. Where are we now? We've done this. So now we are at 3.32. So I'll see you next time.